Welcome everyone. I want to welcome you to the final frontier of the routing protocols, the OSPF. Now OSPF was introduced a while back ago. As a matter of fact, when I took my first CCNA, or my CCNA, well, it will be my first CCNA because you renew every so often. But anyway, the first time I took the CCNA, that was my routing protocol that I had to configure, was OSPF. OSPF is a very large protocol. We talked about it in the previous section. I actually dedicated a section just to OSPF because of its immense size. Now, I will point out the things that you need to know for your certification. I will tell you, hey, this is good to know information when you get out there, when you're taking other certifications. So let's say CCNP, if you're going to go that route. You need to know these things, and when you're out there you will be configuring the things that I'll be telling you about. It's a huge routing protocol. It's a huge routing protocol. Now, we said it was a link state routing protocol, which means it's really, there is no limitations on OSPF. There's no limitations on OSPF except for areas, and we'll get into the terminology in a little bit because we're going to do a little comparison first. As you can see back here, I don't know if you can or not, we're going to do a little comparison between OSPF and RIP. Why RIP? Why not EIGRP? Well, remember, OSPF and RIP are open standards. They can go across different vendors, different manufacturers, where EIGRP is purely for Cisco. So they usually like to compare OSPF to RIP. It's not fair, really. Poor little RIP is being beat up because OSPF will be a bully, I guess, if you compare it to RIP on just the immense size and things that it can do. It's a link state routing protocol. It does create many different things. We talked about it a little bit in the previous section. Neighbor tables, creates topology tables, creates routing tables. All right, it has its own algorithm, just like every routing protocol, called the Dijkstra. Don't ask me to spell it. You'll see it here when we start, when I typed up all these different notes for you. All right, all these things here, I always misspell it. I can never, for the life of me, spell Dijkstra. Okay. So that is the routing, that is the algorithm. Now that algorithm is pretty much linked up, or it uses the topology table a lot to make that shortest path first calculation. And that's another thing. OSPF is very heavy when it comes to the calculations of where to send the information. So it really puts a burden on the router. It is extremely processor intensive. Sounds like a question to me, okay? Processor intensive. So keep that in mind. But, well, one more thing before I continue. As far as the administrative distance, just to throw that out there, is 110. I do have different labs for this. I'm not going to use the same labs that we used before. We're going to use OSPF. It has its own IPv6 lab. It has its own everything. So we'll be using the labs just for OSPF in itself, just to keep everything separate. Now let's compare a couple things. Now you can see here OSPF is a link state, while version 2 is a distance vector. And now we already know that a distance vector routing protocol, all right, distance vector, all it does is based on, hey, direction, which way am I going, and how far is it away. All right, that's RIP. So we're not talking about EIGRP. We know how EIGRP works. But RIP, that's all it's worried about, hop count. There is no hop counts when we come to OSPF. With OSPF, remember, you have a process ID number and you have an area number. The process ID number, for our purposes in the CCNA, it is locally significant. It is used for the stability of the database and keep track of the database that it creates, the link state database. That's the database I'm talking about. All right, so that process ID number, that's what that does. All right, the next number is the area number. The area number has to be the same for the CCNA. Again, I can't stress that enough. You have 4.2 billion areas. LAS, you have 4.2 billion areas. You mean to tell me we're going to only use one? You're going to use one for the CCNA. When you get out there, if you do work for a company that is huge, then you will more likely use multiple area OSPF, and you probably won't be putting area 51, and you won't be putting area 0. Well, you will be using area 0, sorry. You will be using area 0, but What I've ran into, especially in the telecommunications industry, is that they use the IP format for the area instead of the actual decimal for the area. They use a dotted decimal IP format instead of just a decimal number. Like I'm in area 65,233. They get that number and they convert it into an IP. And there's a method for that, but again, you do not need to know that. Can you do it? Yes. Will you do it? Yes. All right? But again, if you're lucky enough to land the job or to be in that position, awesome. You'll see it. If you don't, you'll never see it. All right? So it all depends. It all depends. But for the CCNA, all we need to be concerned with is, hey, make sure the routers are all in the same area. And the numbers don't go crazy to 1,000 or nothing like that. Their numbers in testing, 300, area 0 or area 1. That's the kind of things that they do. Just make sure that we're in the same area. So the limitation of OSPF as far as areas, 4.2 billion. Is that really a limitation? If you want to call it one, okay. Everything has its limits. All right, but we can give it a limitation. If you are using multiple area OSPF, you really don't want to have that huge of an area. Just like you don't want to have that huge of a VLAN, because then you're defeating the purpose of segmenting the broadcast. Well, the same thing goes here. You rule of thumb, 50 routers, let's say, per area. But again, that's a number that I'm throwing out there. So it all depends on your infrastructure and what you do. And interestingly enough, and I want to get off topic, because, I get calls just like everybody else, because my resume is out there, right? Just for the heck of it. Just for the heck of it. And I was looking up today because they keep asking the definition for enterprise networks. And it was funny because there's no real definition for it. There's a very general definition for it. So next time somebody calls you, test them on it. Ask them, what do you mean by enterprise? Is it a size that I'm looking at? Because it's not a size. It is not the amount of devices, but, well, you can say the amount of different devices that is being used, the amount of different protocols that is being used. Because really those people out there that are calling you, they themselves don't know what's going on. All right? So, hey, do not feel intimidated by all these people. You guys know what you're doing. And gals, you know what you're doing. All right? So be confident in what you're doing, in your knowledge, and you'll see that you'll do just fine. Okay? Anyway, supports. They both support classless routing, right? VLSM. So that goes that. Auto-summarization, sorry. OSPF does not auto-summarize. OSPF does not auto-summarize. So we don't have to. In OSPF, we don't have to worry about no auto-summary command. We don't have to worry about it. We actually are going to use wildcard mask. We will put the exact network we belong to. So that's cool. We can do that with OSPF. Now remember, with IPv6, or OSPF version 3, we don't do that. We do it on an interface by interface basis, just like we did RIP version 2 and EIGRP. Okay? But if we're doing IPv4, which we will, that's the first one we're going to do, you're going to see that it's based on network statements. And again, it's using wildcards, and then of course the area. Okay, it does support manual summarization if you wanted to. Raw propagation based on multicast or change. Everything's multicast. But it's based on change. It's based on triggered updates. Triggered updates. Now, the thing with OSPF, though, yes, it creates a topology table, but it does not work like EIGRP, where EIGRP will query the topology table and bring out the next successor, the feasible successor, and everything keeps going. If a link goes down in OSPF, every single router in that area is going to recalculate a new path. So that shortest path first calculation is just not that routers that lost that link. Each and every router, all 50 routers, let's say, in that area, just to throw that number, all 50 routers will recalculate again. So that's the problem with OSPF. Now, they're going to ask you something down the examination. No, they're not. No, they're not. No, they use shortest path first? Sure. All right. No, they're in the same area? Sure. But know that it calculates using the Dijkstra, sure, and it creates a topology table, yes. But as far as what I just said, that all routers will calculate again, no. Know that it's processor intensive, but this is one of the reasons. Imagine, and it's not as quick as EIGRP or even RIP, because of the fact that every router has to recalculate. So if they recalculate, that means that link state advertisements, what is that? They got to send all these link state updates, link state requests, right? All these different things need to be sent in order for the router to make the path again, to recreate everything again. So that is one of the things that with OSPF, it's a little slower than EIGRP, a little slower than EIGRP. Here is based on bandwidth, just like EIGRP bandwidth, where we know that RIP is based on hop counts. There is no limits, like I said. All right, it is faster than RIP. Okay, if you say so. Does support authentication, peer-to-peer, obviously. Hierarchical networks, again, if you're using multiple areas. Will you use multiple areas to create a hierarchy of networks? Of course. If your network is big enough, when you get out there, you will create a multiple area OSPF. A multiple area OSPF. You will do that. Now, I will show you at the end of this section how to create a basic multi-area OSPF. Though you will understand the concept of it, we will do it. But yes, definitely, when you get out there, you will see that. You will not see that on your certification. And remember, this is your goal. This is what you need to focus on. All right, and again, we talked about event triggered. Oh, and there's Dijkstra. That's how you spell it. No matter how much I look at it, there it is, where RIP uses the Bellman forward. So again, a little bit of a comparison, one routing protocol to the other. It's okay to compare, but I mean, that's like a little bully, really, because, my God, OSPF is huge, right? Where OSPF is not very small, all right? So that's a little comparison table. What I'd like to show you next is the actual terminology that you need to be aware of. You need to be aware of. You need to understand what a link is. Two routers connected to each other. That's a link. Two routers that their interfaces are joined, that they build that adjacency, right? That is the former neighbor relationship. That is a link. That is a link. All right? A router ID. That's the name of the router. It's an IP address. The RID is an IP address used to identify the router. It's the name. That's what it is. That's how they identify each other, through the router ID. So it's essentially their name, but in an IP format. Neighbors. This is important. In order to qualify to be a neighbor, you must, remember, we're talking about single area OSPF. The area must be the same. The subnet mask must be the same. Authentication is optional if you want to configure it. And the hello and deads are crucial. This right here, ladies and gentlemen, this one and this one, the area and the hellos. This is something that you really need to pay attention to, because I would test you on that. I would definitely create a test, let's say like a print screen, that I will have one router with a different area, or I will show you a print screen with the default values of the hellos, and then the other one at the bottom doesn't have the default values. So you will say, oh, the hellos are different, because OSPF is extremely picky. If you do not have these the same, and again, this is optional. This is optional. You don't have to have that. You do not have to have that. But if you do, it's got to be identical on both sides. And you'll see that when we do PPP later on in the course. But the hellos and the area are key. And those are things you need to home in. Because if you have a question that deals with OSPF, 9 out of 10, I guarantee you, is going to have to deal with the area, or the hello intervals are not the same. And OSPF, its criteria in order to become neighbors, that must be the same. That must be the same. Again, I stress, in a single area OSPF. All right. Adjacencies, again, a relationship between two routers. A DR. A DR is a designated router. Now, a designated router only comes when there's an election. It has to be in a broadcast environment such as Ethernet. So what is the job of a DR, of a designated router? Because you have designated routers and you have backup designated routers. A designated router, what it does, it creates a full relationship, and we'll talk about that in a second, a full relationship with the rest, with everybody else. Think about a multi-access network, and we have all here. Let me show you. It's no big deal. Here we go. Think about this network right here. Imagine if everybody here had to talk to everybody here and update everybody. It will be chaos. This is Ethernet, broadcast domain, right? They're all touching each other, multi-access network. So now they're all updating each other. They all have full relationships with each other. My God, that's a mess. So what does OSPF do when they find themselves in this scenario? Well, they say, we're going to run an election. And they designate a designated router or a backup designated, and a backup designated router. All right, but when we get into that, we'll get a little bit deeper. All right, but that's what a DR, and it only happens in this type of scenario, multi-access network. But again, this is what I mean by that. All right, so and their whole purpose is that so the DR sends the updates to everybody else, and everybody else updates the DR. That is the main deal. All right, and like it says here, you can control it. And again, I want to talk about it when we get to it, but you can control it many ways. One of the ways that it talks about here is using priority numbers, and they range from 0 to 255. The higher the priority, you're the man. You are the DR. For here to infinity and beyond. No, from here to infinity, right? You are the designated router. One less than that would be the backup designated router. Everybody else will be what they call a DROTHER, designated router other. Who made up that name? I have no idea. Okay, but that's what it is. All right, but anyway, so that's what these two things are, and we'll run into them when we do the lab for that. Hello, that is, and look, multicast, that's how it maintains the relationship between these routers, between their neighbors, because remember, it's the neighbors that talk to each other, and it does it based on multicast addresses. So now, OSPF uses two addresses. If you're forming a full relationship with standard OSPF routers, let's take on a point-to-point connection, you're going to use the 224.0.0.5. But in a multi-access network, you're going to use 224.0.0.5 and 224.0.0.6. The 6 is for the DR and the BDR. So that's why there's two multi-access IP addresses used in OSPF. One for just standard routers, one just for DR and BDR purposes. All right? Know that. Neighbor database, again, a list of all the neighbors, that, their hellos. The topology database contains the LSA packets that have been received. These are your link state advertisements. That within those link state advertisements are all the link state updates. All right? And link state requests and all that. All these link state advertisements, even though they're small, there's a lot of information in there. All right, and when we get to how to become a neighbor, you'll see that. All right, then I just showed you a broadcast multi-access network, which is a network with multiple devices connected to one, just like Ethernet. OSPF areas, contiguous areas. In our scenario, we only have one area that we have to be concerned with. And then you have point-to-point or point-to-multi-point, okay, topologies. So again, but non-broadcast can also be frame relay, all right? And we won't do a frame relay network for OSPF because the whole point for you is to learn what frame relay is. But it does exist. Now, the problem with this is non-broadcast. Well, so is frame relay. So that's why when you get to do frame relay, non-broadcast, multi-access, you run into the same situation of designated routers and backup designated routers. So you need to be aware of these things so when you get into this typical scenario. So there's our terminology, and this will be made available to you. But again, be familiarized with everything, obviously, but there's certain things that you will see on the test, like these criteria, the area and the hellos, all right, the router ID, that you need to know, the DR and BDR, You need to know about these. Okay? All right. So this is the terminology about OSPF that you need to be aware of. Remember, it's a link state routing protocol. There is no auto summary command because it doesn't summarize automatically. All right, we will be putting in wildcard mask. Is based on areas. Areas can go from 0 to 4.2 billion, whatever the whole number is, but it's 4.2 billion. We're concerned with just one single area. And it's using bandwidth. It's using bandwidth that the Dijkstra uses to calculate the shortest path first algorithm in order to find all these different networks and pathways so we can get to our destinations. And thus it keeps that in the topology table. Obviously the best paths, as usual, go to the routing table, and that's how it goes. The only problem is if one link goes, they all calculate again. And once we get to the DR and BDR, the multi-access labs that we'll be doing, and we'll be discussing in more detail with the multi-access OSPF, then we'll talk about that. All right? I'll see you guys in the next lesson.